This week we're going to continue our study of electricity and magnetism and electromagnetism. And last week, the last thing we were talking about was Ohm's Law. And remember what Ohm's Law talked about. It said that basically if you have a battery and you have a resistor in a circuit, and that resistor could be a resistor, it could be something like a light bulb, that the current in that circuit is equal to the voltage or potential difference provided by the battery divided by the resistance. Remember also that current is measured in amps, voltage is measured in volts, and resistance is measured in ohms. So that was the last thing we were talking about in week one. This week we want to continue and talk about series and parallel circuits. A series circuit is a circuit that combines two or more resistors or light bulbs or any other electronic device in a sequential circuit. So in other words, here's a picture of a series circuit, and you'll notice that the electricity coming from the battery would flow through that switch, and then it would flow through that light bulb, and that light bulb, and get back to the battery. So in a series circuit, the current goes through each object sequentially. Now, the resistance of a series circuit is always greater than the resistance of any one of the circuit elements. And it kind of makes sense. If it's hard for electricity to go through one bulb, it's even harder for it to go through two bulbs in a row, or even harder to go through three bulbs. And what that means is that the current in the circuit would be less. In other words, if I have the same battery and I connect that battery to one light bulb, that light bulb will be brighter than if I make it go through multiple light bulbs. Okay, so each of these bulbs would not be as bright as if I just had one bulb connected to the battery. So let me ask you this question. What do you think happens if I unscrew one of the light bulbs? And before you answer that, if we could enlarge what's going on with a light bulb, so if I looked at a picture of a light bulb, there are basically two places that connections are made on a light bulb. One is the side of the bulb, and one is the bottom. And what's actually going on inside the light bulb is one side of the filament is connected to one of those connectors, and the other side is connected to the other. So the current actually flows through the light bulb, through the filament. So what do you think happens if I unscrew one of the bulbs in a series circuit? Well, the answer is that they will all go out. And the reason for that is, you can imagine, if I unscrew one bulb, it breaks the circuit, and that current can no longer flow around through the circuit. Let's look at how we can figure out what the current in a series circuit would be. So one of the things about a series circuit is the current is the same everywhere. And what I mean by that is, let's say that the current leaving the battery is 2 amps. That means everywhere in the circuit, anywhere that I measured the current, it would still be 2 amps. So there'd be 2 amps leaving the battery, 2 amps going through my first resistor, 2 amps going through my second resistor, etc. The other thing that we know about a series circuit is that the sum of the voltages across each resistor is equal to the total circuit voltage. So for example, if my battery is putting out a voltage of 10 volts, let's say that R1 has a voltage across it of 6 volts, and R2 has a voltage across it of 3 volts, then R3 would have to have a voltage across it of 1 volt. In other words, 6 plus 3 plus 1 is equal to 10. Now, in terms of what the voltage across each would be, that depends on the values of the resistors. The other thing that's true for a series circuit is that if I want to figure out what is the equivalent resistance of these 3 separate resistors, the equivalent resistance can be found by just adding each of the resistors together. And the reason that I might want to do that is I would like to know what one resistor could replace those three resistors and have the circuit be the same. And effectively, that's going to allow me to figure out what the current would be in that top circuit. So let's take a look at an example of that. So here we have a series circuit. It says a series circuit contains three resistive elements, or resistors, that have a value of 4, 6, and 8 ohms. And the question is, if the voltage is 110 volts, what's the total resistance of the circuit, and what's the current through the circuit? Well, for a series circuit, we know that the equivalent resistance, in other words, the one resistor that I could replace those three with, is just the sum of the individual resistors. So to work that out here, I have a 4 ohm resistor plus a 6 ohm plus an 8 ohm, and that comes out to a total of 18 ohms. So that would be the equivalent resistance. Now, if I want to find the current through the circuit, what I want to think about is that I've just figured out that I could replace those three resistors with one equivalent resistor with a value of 18 ohms. Well, I know how to find the current in that circuit. Current is just equal to voltage divided by resistance. In other words, that's Ohm's law. And so if I take my 110 volts and I divide it by the resistance of 18 ohms, if I do that on my calculator, I get 6.1 amps. And that is the current through the circuit. So in other words, that's the current right there, that's the current here, that's the current here, that's the current there. The current everywhere in a series circuit is the same, and we've just figured out that it's 6.1 amps. Let's take a look at a parallel circuit. In a parallel circuit, each bulb has a direct connection to the battery. In other words, you'll notice the current comes around, and when it gets here, it can either go through that light bulb and back to the battery, or it could go through that light bulb and back to the battery, or it could go through that light bulb and back to the battery. So each light bulb is effectively independently connected to the battery. And you'll notice that in this case, each bulb will be as bright as it would be if it were the only bulb connected to the battery, because essentially each bulb is directly connected to the battery. We're not making the current go through one bulb, then another bulb, then another bulb, like we do in a series circuit. This also means that if we unscrew one of the bulbs, it's not going to affect the other bulbs. And we can see that here. You'll notice that this switch is open and that bulb is not lit up, but the electricity has no problem going through that bulb or going through that bulb. So in a parallel circuit, if you unscrew one bulb, the other ones don't go out. So let's take a look at what else we know about parallel circuits. And in this case, I now show three resistors in parallel. And again, you'll notice they're in parallel because when the current comes here, it can either just go directly through that resistor and back to the battery, or it could go through this resistor and back to the battery, or through this resistor and back to the battery. So essentially each resistor is directly connected to the battery, and even if I wipe one out, there's no problem for the electricity to go through the other two resistors. Okay, so the sum of the currents through each resistor is equal to the total circuit current. And what we mean by that is simply whatever current is leaving the battery, when it gets to this junction, it's going to split. And then when this current gets to this junction, it's going to split again. And then it's simply going to come back together. So whatever current leaves the battery gets split into the different resistors and then comes back together. The voltage across each resistor in a parallel circuit is the same because, again, it's as if they're each directly connected to the battery. So if the battery is 10 volts, then the voltage across each one of these is 10 volts. Now let's say that we wanted to figure out what's the one resistor that we could replace these three with and still have the same current being drawn from the battery. The way that we figure that out for resistors in parallel is with this formula. And you'll notice it's a little bit more complicated than resistors in parallel. And so let's do an example where we see how that works. So here's my problem. I have a parallel circuit containing three resistors with values of 4, 6, and 8 ohms. So let me just draw the circuit. So let's say I've got a resistor of 4 ohms, and then in parallel with that I have a resistor of 6 ohms, and in parallel with that I have a resistor of 8 ohms. And I've got a voltage of 110 volts. And what I want to figure out is what is the total resistance of this circuit. Well, to do that, I'm going to use that formula that 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Now, students often get confused with this formula. Let's go through it. So 1 over R equivalent is equal to 1 over 4 plus 1 over 6 plus 1 over 8. Now, you could do, find a common denominator to add those fractions, but you can also just convert them each to decimal and add it. In other words, take 1 divided by 4, which is 0.25, take 1 divided by 6, and 1 divided by 8. And if you do that and add those up, you'll find that 1 over R equivalent is equal to 0.5417. And I've just rounded off. It actually goes farther, but that's fine for our needs. Now, notice that's not what you want. That's not the answer. That's 1 over the equivalent resistance. So what I now do is I swap those two. In other words, that means that R equivalent is equal to 1 over 0.5417. And if you work that out, what you should find is that it's equal to 1.85 ohms. Okay? So please do that calculation on your own and make sure that you can show the equivalent resistance of this circuit is 1.85 ohms. In other words, if I were to replace those three resistors and have the circuit be equivalent, meaning the current is the same as the current here, then I would need a resistor of 1.85 ohms. Once I've got that, I can find out what the total current in the circuit is, because current is equal to voltage divided by resistance. So that's 110 volts divided by 1.85 ohms. And if you work that out, you'll get 59.5 amps. Now, just to make it clear what we found, that would actually be the current leaving the battery in the original circuit, as well as the current in our equivalent circuit. Now, once the current gets to the resistors, remember it splits into different pieces, but this would be the current leaving the battery in that circuit.